right. Thanks, everybody, for coming. Thanks to Rakuten for hosting us. Thank you, Luca, for the kind introduction. All right. So GANs are, there's a lot of different ways you can approach GANs. You can talk about GANs. And for that matter, there's a lot of different ways you can talk about deep learning or machine learning. Last time I was here, I went through a super detailed, from scratch, how to code up deep neural networks from scratch style of talk. And that's more difficult to do with GANs because they're intrinsically more complicated, number one. And number two, there's, I think, just from talking to people already, there's a wide range of levels of familiarity with this stuff in the audience. So I'm kind of curious just to get a sense of where people are. Who here thinks, who here actually does machine learning, like for their job? Okay, cool. A lot of you. Nice. How about stuff with neural nets or deep learning? Who actually does that for their job? Cool, cool. Not as many, which is totally fine. How about, even for those of you that didn't raise your hand, who here thinks they could, I won't make you do it, I promise, who here thinks they could stand up and explain what a neural net is right now if I like cold called you? Okay, most of you. Very cool. Or, about half of you, I'd say. All right. So I think this is about the right level then for this talk. I'll breeze through what neural nets are, give a high-level overview of what GANs are, then get a little bit into the nitty-gritty and some of the details that you need to understand if you're going to build them. And then also sprinkled throughout, I'll talk about some of the cool cutting-edge results that we've seen with GANs, and then at the very end speculate on where they might be going in the future. So hopefully you'll find it interesting. Okay, so what are GANs? What makes them work? What are the latest and greatest cutting-edge results? What is their future? All right, so high level, GAN stands for Generative Adversarial Network. They're a method of training neural networks to generate images, and they're trained by an adversarial process where there's two neural networks that are sort of competing against each other. That's a really high level what they are. What is a really basic example of what they can do? Well, who here, let's just get a show of hands, who here is familiar with the MNIST data set? Okay, everybody, right? You can generate MNIST digits using GANs, right? Handwritten digits. You can, these are not actually real digits written by humans. These are generated by a neural network that has learned what images of digits look like. For a more cutting edge example, this was just published in October of 2017. Some researchers, and we'll talk about how this was actually done near the end of the talk. Some researchers at NVIDIA published sort of the closest thing we've seen yet to photorealistic GANs. These are actually not real people. These are images of people that were generated by a GAN that had been trained appropriately. These are 1024 by 1024 images, and they look pretty photorealistic. Now, to be fair, these could have been sort of handpicked by the authors of the paper, but still, it's incredibly impressive. All right, so taking a step back, let's start with the basics. So GANs are this form of neural network. So what are neural networks? So if you've read online or tried, somebody asked me on the way in, like, are you self-taught with this stuff? And with neural networks and GANs, you sort of have to be, unfortunately. And if you go online and try to read about what neural networks are, you'll inevitably come across diagrams like this that say, well, they're just that. They're just circles with arrows connecting them. And I've sort of tried to demystify that, and that's what my whole last talk was about, like getting into the nitty-gritty, talking about what they actually are. But for now, I'll just stay at a high level. So mathematically, neural nets are just functions. They take in input and produce output. They're nested functions, so they take input and produce some intermediate values. Then they take those intermediate values, apply another function, produce some more values, et cetera, and eventually you get output. They're universal function approximators. They can be used to approximate any function, differentiable or non-differentiable. But they are themselves differentiable. So the whole function that's generated, you can compute its derivative with respect to any input, any parameter, anything like that. All right. So if you have like layers of a neural network, L1, L2, and L3, you could write a neural network like this. You could write it as a input comes in, let's call it X, goes through L1, then that goes through L2, then that goes through L3, and then you get some output. And there's also weights, let's call them V and W in there. And you could write the output of a neural network as a function of that, or you could write the loss of a neural network as a function of that. Okay, I think a lot of people are probably familiar with this. So there's just some mathematical function. What does differentiable mean? It means that you can compute the derivative of the loss with respect to the weights. And what does that mean? That means that you can actually train these neural networks via gradient descent or backpropagation, which is like gradient descent upon gradient descent. Importantly, though, not only can you compute the derivative of the loss with respect to the weights, you could also compute the derivative of the loss with respect to the input to the neural network. You could figure out if I changed the input by this much, if I changed a pixel in the input image by this much, how much would the loss change? Would the loss go up or down? You can do this because neural networks are differentiable. And this turns out to be key in understanding how GANs work or why they work. So what is the origin story behind GANs? Well, this guy was at a bar and he invented GANs. That's actually what happened. Okay, but sort of taking a step back. So Ian Goodfellow is the inventor of GANs. In 2013, he was at the University of Montreal. He was a grad student studying under Yoshua Bengio, who's one of the leading neural net researchers of all time, in the world today. He's the only leading neural net researcher who is not at Google or Facebook. He is still a professor at the University of Montreal to this day and still advises grad students. These two guys were going to run a speech synthesis contest. So who could produce a model that could generate artificial speech that sounded human? And they said, okay, we'll have a neural network listen to a bunch of speech, real speech and fake speech, and learn to discriminate between real speech and fake speech. And that's how we'll judge the contest. We'll judge whether people can submit things that can fool this neural network. But they decided actually not to run the contest because they ran into this problem of they figured people would just try to game the system. They would just generate speech that didn't necessarily sound human, but just fooled this particular neural network. And so they said, okay, well, we don't really have a good way of discriminating here, so we can't do it. Then Ian Goodfellow was in a bar one night, at least as he tells the story, and he asked the question, can we change this whole thing by making the Discriminator Network, as it ended up being called, actually learn? So it can hear fake speech that is trying to be real, and it can then learn that that's fake. And then it can get more, as it hears more and more fake speech, it should eventually learn, oh, it should get better and better at distinguishing between fake and real speech. But then he thought, well, people could try to game that, and that's where the idea of GANs came from. So let's go into how they actually work and what actually resulted from that insight. So here's how GANs actually work. You start off with some random vector. And this is how you generate these neural nets that can produce images that are real. You start off with some random vector. And you feed it through a neural network that has, and I'll get into this in excruciating detail in a bit, that has this deconvolutional architecture, which means it takes a random vector, does a bunch of transformations to it, and you end up getting an image, right? So you could take in a 100 unit vector and end up with a 784 units and reshape that into a 28 by 28 image. So it's some neural network that's, again, just a function that can take in 100 and output 784. And if let's denote the matrix of pixels that it generates X. Then you feed this generated image into a second network. And with this second network, the researcher, the person who's running this, knows that this image is fake, knows that it's generated. So what you do is you feed this through the second network and you compare whatever this network outputs to the value of 0. Because you want this network to produce 0. you want every time this network gets a fake image for it to say it's fake. So if the network that you fed this random image through the network, if it produces 0.3, that's bad. You give it a penalty because it didn't produce 0, and you use that penalty, that loss, to update the second network. Because you want it to output 0 every time it gets a fake image. And this network is called the discriminator in the Generative Adversarial Networks framework. Yes, yes. Second one's the discriminator. Yep. Then, and this is where the differentiability of neural networks comes into play, you also compute this quantity, which is how much the loss, how much each of those input pixels that were fed into that second network affected that loss. And then you do this clever trick where you use the inverse of that to train the generator, the network that's generating images. Why do you do that? Well, the generator wants the discriminator to output 1. It doesn't want it to output 0. It wants to be feeding the discriminator images that the discriminator thinks are real. So you use the negative of this loss, which is how much each of the input pixels to the discriminator affected the loss. You use the negative of that to train the generator. And you feed that back through and use that to train the generator. Then you generate a new random input vector and repeat this process over and over again. So that's most of how GANs work. So what's missing here? In the back. Yes, exactly. How would the discriminator ever get a 1? What's going to happen here is the discriminator is going to get really good at saying that fake images are fake. But the reason GANs are so tricky and sensitive to hyperparameters and so on is that you have these two neural networks and they sort of have to get smarter at the same rate. So you have to do something else to, yeah, there we go. What's missing? So this will train the generator to generate very good fake images, and the discriminator to get really good at saying these fake images are fake, but the discriminator also has to learn that what a real image looks like. So part 2 is what you do is you also, sort of separately, give the discriminator real images, but this time you compute the loss comparing the value of what the neural network is outputting to 1. Because every time it gets a real image, you want it to output a 1, right? We want the discriminator to be such that every time it gets a fake image, it outputs 0, and every time it gets a real image, it outputs 1. So it says fake images are fake, real images are real. So these are sort of the two big steps. Feed it fake images, compare the loss, compute the loss by comparing the prediction to 0, and then the second part is do this with real images. This is a quote from the original paper on GANs. I'll just read it because it explains it very concisely. The generative model can be thought of as analogous to a team of counterfeiters trying to produce fake currency and use it without detection, while the discriminative model is analogous to the police trying to detect the counterfeit currency. Competition in this game drives both teams to improve their methods until the counterfeits are indistinguishable from the genuine articles. And here's a cool aside. This is actually the original GitHub repo with the code that Ian Goodfellow used to code up the first version of GANs ever that generated MNIST digits. This is from his private GitHub repo that he made public when he got his PhD from when he was a grad student at the University of Montreal. So there's a link to this in the talk. All right. So there's a link to this notebook, which is in the folder as well. This is actually running a GAN on AWS right now. And we'll come back to that at the end and see the images that it's generated. All right. So what are the things that makes GANs, what makes them work? Well, Here we're going to get into the nitty-gritty a little bit. One thing is that's made them work well is you have this deep convolutional neural network architecture. That's key to making GANs work, both in the generator and the discriminator. The discriminator, which is just a classifier, is a deep convolutional neural net, and the generator is a deep sort of deconvolutional neural net. And second, there's this trick called batch normalization. So first, let's sort of go through convolutions a little bit and talk about what they are, why they're important, and so on. And then we'll talk about what deconvolutions are. All right, so convolutions. Again, with these diagrams, if you ever tried to understand what's going on in neural networks, you might have seen diagrams like this, like, oh, a convolutional neural network, it's just that. But let's actually unpack that and figure out what's going on. By the way, this is the famous AlexNet architecture. This is the first successful convolutional neural net architecture that was used on the ImageNet data set. It actually, this architecture has its own Wikipedia page. So that's pretty unusual for a neural network architecture. So what's going on here? You have these input images, which are 224 by 224 red, green, blue images, so 224 by 224 by 3. And then you have this next layer that's 96 deep. So what does that actually mean? So what's going on with convolutional neural nets? At a really high level, you have these filters, which are slid over the image via the convolution operation. And these filters end up being feature detectors. They end up detecting whether there's an edge here, or later on in the network, whether there's an eye here, or so on and so forth. And after the network has been trained, you can visualize these filters. That's what that says. So in the AlexNet architecture, concretely, what actually happens? The input is 224 by 224 by 3. It's by 3 because there's red, green, and blue channels. So what actually happens is each of those 90, so there's actually 96 times 3 filters, and each one of the 96 filters is, there's one component slid over the red channel, one component slid over the blue channel, and one slid over the green channel, and then that's outputted. So that's the output of doing that convolution operation. And there's 96 of these filters, and they're each 11 by 11. So the result of that is that you can combine these filters, the red, green, and blue components of the filters, each of the 96, and get a little mini 11 by 11 image. And these are the actual filters that were learned in this famous neural network architecture that won an image recognition competition. Now, many of you might, if you've read a little bit about convolutional neural networks, you might have seen this visual before. What you might not know is if you zoom way in and you actually look at these, you can actually see that these are indeed 11 by 11 images. There's 1, 2, 3, there's 11 pixels by 11 pixels in each of these images. So these are the actual sort of features that were detected in this neural network. So that should give you a little bit of a concrete idea of what's going on under the hood when I say there's a convolutional neural network going on. All right. So there's another thing, and this ends up being a really tricky thing when you do GANs. You have to have all the convolution operations and then all the deconvolution operations result in the right image size being outputted. Convolution operations, they change the image size. And the reason they change the image size, the extent to which they change the image size turns out to be a function of how much padding you use, so how many zeros you use around the edge of the image, how big the filter is, how big the stride is, and so on. And let's look at a couple examples here. So there's actually two, I'll show a little GIF in a second. There's two sort of key terms when it comes to padding in particular in convolution operations. One is called same padding, and that means that basically, let's say you start out with a 5 by 5 image, and you have a 3 by 3 filter that you're convolving with this image. Well, if you know you want your output to also be 5 by 5, what you do is you put, since the filter is 3 by 3, you put padding of 1 around the edge of the image. And what that ends up doing is that ends up making the output of this convolution operation also a 5 by 5. So that's why this is called same padding. because you end up with the same image size after you do this operation. Just a term that's good to know, and I'll come back to it when I talk about deconvolutions. There's another term which is called valid padding, and this it basically just means use no padding. I don't know why it's called valid. It just means no padding. So let's look at an example here. With valid padding, you're always going to end up with the output image being smaller than the input image. So why is that? Kind of looking at this concrete example, we start out with a 4x4 image, and if we slide a 3x3 filter over this image, you can see that because the filter sort of gets stuck at the edges of the image, you end up with a 2x2. So you start out with a 4x4, and you end up with a 2x2. And so that image gets smaller as a result of not using any padding or using what is in neural network terminology called valid padding. All right. So there in the documentation that I linked to, which has an excellent and really detailed overview of convolutions, there are these formulas you can memorize for how the input size and output size changes as a result of changing the padding. It's working now. Yeah, I think it's good. Nope. Oh. Okay, we're back. All right. Give it up. Give it up for Pino, everybody, changing the battery on the fly. There you go. All right. So there are formulas relating these things. I think you don't usually, I wouldn't recommend memorizing them. You can just sort of reason your way through, okay, if I have this input size and I apply this convolution operation, what output size am I going to get? And if you're ever actually building GANs, this becomes extremely important. So one reason this becomes tricky, with convolutions, it's actually pretty straightforward. The question is, how do we reason in the same way about if I start with this input, I end up with this output? How do we reason in the same way about deconvolutions? Like that is just a concept that doesn't seem to make as much intuitive sense. Well, one way you can think of, in order to reason about these deconvolutions, you actually have to think about convolutions in a different way. You have to think about them, and I'll show why this makes sense in a second. You have to think about them as matrix multiplications where most of the values are just 0. So why would that make sense? Well, oh, that's right. Well, if you think about this example we just went over, where a 3x3 filter was slid over a 4x4 image and we ended up with a 2x2. Well, that's some operation that's taking a 16-dimensional vector as input and outputting a 4-dimensional vector, right? It's taking in 16 as input and outputting 4. You can represent that with a matrix transformation, right? You can represent that with a 16x4 matrix. And therefore, and this is actually below, this is the matrix you would use to represent that. You can see that most of the values are 0. And any convolution operation, even an operation that transforms some huge image into, I don't know, some really tiny image, can be represented as a matrix multiplication, but with most of the values being 0. So what are deconvolutions? Deconvolutions are just the inverse matrix transformation, as it turns out. So when you're building GANs, in particular when you're building the generator, what happens is you start out with some vector, and you have to successively apply these deconvolution operations and end up with an image that's exactly the right size to be able to feed it into the generator. And this actually, if you don't understand what's going on with deconvolutions, this is actually really tricky. It's like you're trying to jump and then land at exactly the right place. So being able to reason about them properly is important. And the way you should think about deconvolutions is if you know you want to end up here, you sort of have to think about, if I start here, like what operation would I have to apply to get there? And that can tell you how to get backwards from here to here. I'll go over an example. So if we start out with a 4x4 image, some error, and we apply a deconvolution operation to it, so if we do a deconvolution operation on a 4x4 image, we end up with a 4x4 image. And that kind of makes sense, right? Like, oh, sorry, if we do a deconvolution operation with same padding, we end up with a 4x4 image. And that sort of makes sense. If you start out with a 4x4 image and then apply same padding to it, then you're going to end up with a 4x4 image. So going the opposite direction, starting out with a 4x4 and applying a deconvolution with same padding should result in ending up with a 4x4. And then you get these counterintuitive results like, let's zoom out another one here. If you apply a deconvolution operation with valid padding, which is like no padding, if you start out with a 4x4, you end up with a 7x7. Oh, in this case, the filter size is 4. So why would that be? And the reason ends up being that if you start with a 7x7 and then apply a convolution operation with no padding, so with valid padding, with a 4x4 filter, then you end up with a 4x4. So when you apply the inverse operation to a 4x4, you end up with a 7x7. And that's sort of how you have to reason about deconvolutions. So for those of you that ever have to actually end up building GANs, this is something that definitely caused me a lot of headaches, and I think causes a lot of people headaches when they're learning this stuff. So hopefully this clears up that point. All right. So this is sort of an, oh yeah. Yeah, that's a great point. So you don't have to, there's nothing written that says you have to use convolutions and deconvolutions to do a GAN. This framework could work with any kind of neural network architecture. It so happens that deep convolutional nets and with these deconvolution operations work best with image data, which is the majority of where GANs have been applied. I will also say, for generative modeling more generally, there are other kinds of neural networks that have been applied. But for this adversarial process, it's really just convolutions and deconvolutions. Like there are generative models that use recurrent neural networks to generate images, but they're not really using an adversarial process. Yeah. Mm. Yeah, could be. That's a great point. Yeah. Yeah, they're a combination of a neural net. I think a decent way to think about it is the generator network is sort of the inverse of the discriminator network. It's trying to do the inverse operations, basically. Yeah. 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 I'm not too familiar with using recurrent neural networks in an adversarial process. There's like a really cool paper from DeepMind where they generated images using a recurrent neural network by sort of having the recurrent neural network read the images row by row and generate them that way. But maybe there's more on like language using recurrent neural networks for language modeling. I think you had a question? Yeah. Yeah. One more question from this guy here, and then we'll move on. Yes. I'll repeat the question so everyone can hear. He asked about if you use stride of greater than 1. So in all of these examples, we're only moving the filter by 1 unit as we do the convolution or deconvolution. If you use stride of greater than 1, then this becomes more of an issue and it's harder to figure out. It's just you have to think a little bit more to figure out what the output size will be, or whether you're doing a convolution or a deconvolution. But yeah, so that's correct. All right. I'll move on. So this sort of illustrates the idea that I was talking about. You can represent convolutions as a matrix transformation. So whether you're using same padding or valid padding, if you think of the operation going forward as as being represented by a matrix transformation, essentially you're applying the transpose or the inverse or the transpose of that matrix, not the inverse, to do the transformation going the other direction. So if you understand that, doing these deconvolution operations will make a little more sense. So that's an explanation of the 4x4, 7x7 thing. Yeah, and I'll check out our generator network and see how it's doing at the end of the talk. But you can look at an actual example of the generator architecture in the that should be generating MNIST digits right now. All right. The next trick, sort of innovation that's allowed GANs to really work well, is a trick called batch normalization. And it's a really powerful and pretty simple trick that just works extremely well, and it's pretty easy to understand. So consider a deep neural network, right? You've got a bunch of layers here. They're all connected. They could be convolutional or not. We know that normalizing the input to a neural network usually helps it learn, right? If one feature is on a scale from 0 to 1 and another feature is on a scale from 0 to 1,000, then ultimately the neural network is going to have to learn that one feature seems to be having, for every unit change in that feature, it seems to be having 1,000 times more impact than the other feature. So scaling our data helps the neural network not have to learn that. Well, it turns out that applies further down in the neural network too. So if you think about what's being fed into the third layer of this neural network, it's a bunch of numbers. And the same argument applies. The neural network should, in theory, not have to learn that changing a feature that it's getting by 1 unit, it shouldn't have to learn the various scales of the features that it's being inputted, or that it's receiving as input. So intuitively, it's sort of intuitively, batch normalization should work for the same reason that normalizing data into our neural network works. So what is batch normalization? What is it actually doing? Well, so normally when we pass data through a neural network, we don't just feed one observation at a time. We don't just feed the entire data set through. We feed batches through. We feed 64, 128 observations through at once at the end of the slide, yeah. So for that batch, so let's say, so we're feeding 64 images through our neural network. We get to the end of some layer, and all the elements in that layer have a value. What we do is we just take those 64, if there's 100 features, we take those 100 values, we take their mean, subtract it off, and divide by the standard deviation of those. So that at every layer of the neural network, what we feed forward ends up being mean 0 and standard deviation 1. And this ends up working incredibly well. This was discovered in mid-2015, and it's a really powerful trick for these deep convolutional neural networks. Yes? Yeah, that's a great question. The question is, why don't we pass one data point at a time or pass the whole data set at once? I don't know if there's a short answer. It has to do with, these networks are trained by a gradient descent, and the trade-off is if you feed one data point through at a time, you're going to be taking perhaps too erratic of steps to find the local minimum, whereas if you feed in the whole data set at once, number one, you could run into memory issues in the case of large data sets, but number two, you could just sort of be going like at the same direction at every interval. So there's no magic. It's a great question because for a lot of the hyperparameters used in neural networks, there's nothing written in stone that says these are the best hyperparameters to use. It so happens that batches of around 64, 128 work well for a lot of deep neural networks. They tend to find the best balance between that trade-off of getting towards the minimum of whatever you're trying to find with stochastic gradient descent without going like in the same direction every time as you do if you went and if you fed the whole data set through. So you might miss local minima. But so it's a great question. Yeah. Yes. Yes. His question was, is it important for the sorting of the data to be randomized for batch normalization to work? Yes. And in fact, in general, for training neural networks in batches, it's important for the order of the data to be randomized. This is a classic here's a classic beginner's mistake. If you're training a neural network on MNIST digits, right, to recognize whether a digit's 0, 1, 2, 3, or 4, if you don't randomly shuffle the data, what you could do is you could you could see training accuracy going like this, going up close to 100, then crashing, and going up close to 100, then crashing, and going up close to 100, then crashing. Why? Anyone? What? It could be that it goes all the way back to the beginning, but it's actually what I was thinking is this. You first feed all the zeros through. The network really gets good at identifying zeros, then you start feeding the ones through. And it gets really good at identifying ones, then you feed the twos through, et cetera. So if you do that, you could get these really weird looking training curves. That's a classic beginner's mistake on MNIST, for example. So yeah, in general, you should always shuffle your data. I'm going to move on. I'll be sticking around for questions at the end. All right. I want to get to a subtle point with batch normalization. Can anybody think of an issue? This is really subtle. Can anybody think of an issue with doing batch normalization with convolutional neural networks? Hmm. Yeah. Yeah. I think Luca is on the right track. So what are the actual neurons in a convolutional neural network? Here's like one 11 by 11 filter from AlexNet. The neurons are functions of these individual elements here. So the actual output of this, of convolving this with the image, will be an actual image. That'll be, let's say, 96 by 96, let's say. Each one of those 96 by 96 pixels is a neuron. So if we change one pixel by a different amount than its neighboring pixel, then the image will look it could sort of destroy what the image looks like. And what the image looks like is what actually matters. So instead, what you do in convolutional neural networks is you take the average, you make sure that all the pixels in an individual image are changed by the same amount. So let's say you have a batch of 64, you're feeding through a neural network, and you have one image that's 96 by 96. What you do is you take the average pixel value for all 64 images for each of those pixels in that 96 by 96 image, and change all the pixels in the image by the same amount and divide them by the same standard deviation. So subtle issues. So there's actually more you have to do with batch normalization in convolutional neural networks. Yeah, and that's what this does. The original, what do you mean by the original? Yeah. Mm. Yeah. Yeah. Luca's question is, what if the original values of the image are like 20 or some scale that's not mean 0, standard deviation 1? I think the answer is, in theory, the scale that you use when you feed in images to a neural network, either at the beginning or at any layer, shouldn't matter. It's only the relative values of the pixels that should matter. So the answer is you start it at the beginning, because if your original image has pixel values ranging from 20 to -20, you would just scale that anyway before you even start. I see what you're saying. Then at the if you knew that your output image had to be between -20 and 20, you could multiply by 20 at the end. That's a good point, yes. All right. So there's actually another step with batch normalization that allows the learning to be even more flexible. Instead of just using the normalized pixel values at each step, you actually have these other parameters, and you multiply the normalized pixel. You have these parameters gamma and beta, and you initialize them to 1 and 0. So you're starting out by just letting the network use the normalized pixel values, but you're letting the network potentially learn to use more than 1 as the mean, or less than, more than 0 as the mean, or less than 1 as the standard deviation, and so on. And there's technical reasons why this works that I'll let you read about, but I'll skip over for now. All right, so I know that was a lot of technical stuff. So now I think there's like a cool example of what GANs have been able to do. That this was an idea submitted to, accepted and presented at NIPS, the Neural Information Processing Systems, the largest conference on this stuff in the world, in 2017, and it's called Pose-Guided Person Image Generation. And it's both a really cool result, and it's based on a really cool data set. And I'll go over the data set too as well. So it's based on this data set called Deep Fashion. And a bunch of researchers, they're researchers at the Chinese University of Hong Kong, as well as some research institutes in Asia. They got a bunch of pictures of people wearing different items of clothing. And they got different characteristics, like where the people's body parts are located in the images and so on. So it's this massive data set. And here's a really cool visualization from the data set. So this is a picture. And we have like all the different parts of this woman's body, like her elbow, her wrist, and so on, tagged. And what this visualization is this is for all the images in the data set where the location of the left elbows are in the image. So you can see that they tend to be on the left, they tend to be in the upper part of the image, et cetera. And you also have the left sleeve, where that is in the image. And you can see, again, that it's mostly on the left, mostly toward the upper part of the image. Sometimes the person's turned around, so it's actually the left sleeve is on the right side, et cetera. So this is a really cool data set. What I'm about to show is only one example of things people have done with the data set, but yeah, there's a lot of cool stuff here. So pose-guided image person generation. It is what it sounds like. The researchers figured out a way to use GANs, as well as other neural network techniques, to take an image of a person and change their pose. So here's an example. They have this model standing, against a white background, and they defined a pose here. So the pose here turns out to be her turned around. And the GAN, using a bunch of information like from the data set, so original images as well as poses that they wanted the GAN to be able to generated this image, which is like her actually turned around in the correct pose that that the researchers wanted. And then the researchers used another neural network, which is just a neural network that's used to sharpen images. So this is a very common thing researchers have done with neural networks. You can take a bunch of sharp normal images, blur them a little bit, and then get a massive training set of sharp images and blurry images. And then you can train a neural network to take in blurry images and try to sharpen them up. So that's what researchers did here. They sharpened this image up, and they got like a generated image of this woman in this pose. And that's compared to the ground truth here. So it's interesting. It nails the pose. When you see this, and it's not so blurry in the projector, you can see that it's pretty high resolution. One thing that's anybody notice something wrong about this image? The straps, missed the straps, right? There wasn't a notion of, okay, this is a top with straps, and I should therefore put straps on her back. It wasn't like that just didn't, the neural network couldn't figure that out, but still, it did a pretty good job. And I chose this image randomly, by the way, from like all the images that were in the paper. So this wasn't a cherry-picked best example or anything. I thought this was really cool. It turns out this actually works in like natural settings, not just a model with a white background. So here's this woman wearing a backpack. Here's the pose that they were trying to generate. The GAN generated that. And the neural network that was trained to sharpen images generated that. And here we have the ground truth here. So again, there are some details that were missed, right? She doesn't have her bike in the image that was generated, even though she had a bike. Or it looks like she actually can't tell if she has a bike there. The straps on her backpack are definitely missing. That's a more obvious one. But yeah, one example of the cool things people are starting to do with GANs. Okay, so that's sort of what people have done with GANs. What like new research areas are going on with GANs? Well, I think one of the, and like more generally, you might ask like, what possible use could this have? This is like a cool science experiment, but who cares? And one of the big uses of it in deep learning and machine learning is this, this application to a subfield of machine learning called semi-supervised learning. So what is semi-supervised learning? Let's see how we're doing on time. Okay, cool. So semi-supervised learning is a third type of machine learning other than just supervised learning or unsupervised learning. At a high level, supervised learning, you have labeled data. Unsupervised learning, you have unlabeled data. So semi-supervised learning is all about, can we learn both from labeled data and unlabeled data? And it turns out that you can with GANs. All right, so how does that work? Well, let's consider a basic, discriminator network you're trying to build to figure out whether a digit is 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, a typical setting for supervised learning. So we know how we can learn from labeled data there. How can we learn from unlabeled data? It turns out you can do the following to make this work with semi-supervised learning. You just add an 11th class that you're predicting at every point, which is whether the image is real. So for real images that are labeled, you feed through a vector of all zeros, 1 with the actual image label, and 1 for real, if it's a real image. For fake images, you just feed through all zeros and probability of real also 0. And then you can also learn from real unlabeled images in this way by feeding through all zeros and then 1 for real. And this allows you to learn from both labeled and unlabeled examples. In practice, using real unlabeled examples is a lot less effective than using just fake examples and telling the network that they're fake. And since we're a little short on time, I'll just say there's a way that you have to train the generator that generates these fake images for semi-supervised learning that's different than the way you typically train the generator, and it involves something called feature matching. So there was a big paper that proposed this whole semi-supervised learning approach in 2016 called Improved Techniques for Training GANs, and they proposed this thing called feature matching. And the idea is basically when you feed fake and real images through this network, you look at the last layer of the network right before you make the prediction, and you use the difference between the values of this last layer for the real images and the fake images and feed that back through the network as your loss. And it turns out this works better than just using a traditional generator loss. Something that's very interesting, and this goes over sort of exactly what that is. Something very interesting, the researchers, this is a quote from the actual paper. You might ask, why does this work? They don't really know. The approach that introduces an interaction between the discriminator and the generator, this approach introduces an interaction that we don't fully understand yet. But empirically, we find that optimizing G, the generator, using feature matching works very well for semi-supervised learning, while training G using GAN with mini-batch discrimination does not work at all. And they say to figure out why this is, that's left for future work. So there you go. Good luck, as Luca said. All right, and by the way, so what was the result of this? There's a famous data set called the Street View House Numbers data set that takes images in the wild taken from Google Street View. And using all 600,000 images in this data set, you can build a classifier that's over 98% accurate. With this semi-supervised learning approach in 2016, the big breakthrough was they built a classifier that was over 94% accurate with only 100 labeled images from each class. Only 100 zeros, 100 ones, 100 twos, and so on. So only 1,000 labeled images total, they were able to get over 94% accuracy, which was huge. So if you wonder sort of where are GANs being used, what is like the biggest implication of them for machine learning, it seems like it's enabling people to learn without first compiling massive data sets. This approach of you learn from the images that you have, as well as having the GANs generate synthetic data that your classifier or your algorithm can also learn from. It seems like that's the most promising application of GANs that we've seen yet. So what about sort of big breakthroughs on GANs themselves? Well, now we're going to get back to what we talked about at the beginning of the talk, this idea of progressive GANs. So some researchers at the NVIDIA Research Institute published this result just in October of 2017. And it was sort of by far the closest we've ever gotten to producing photorealistic GANs, GANs that can actually produce photorealistic images. And it even made the front page of the New York Times. Not the front page, I'm sorry, the front page of the text section. This is the New York Times headline from January of this year, or from last month. All right, so how did they do it? The main idea is, it's this interesting idea. So they're called progressive GANs, and the paper was called Progressive Growing of GANs. So what they did was, and it's sort of wild and interesting that this worked, they originally downsampled these 1024 by 1024 images to just 4 by 4 images, 16 pixels. And they trained a GAN to just generate good fake images at that resolution, 16 total pixels. Then they got 8 by 8 image. Then they downsampled the real images to be 8 by 8 pixels. And they used a combination of the GAN that had already been trained to generate 4 by 4 pixels, 4 by 4 pixel images, and used it to generate high quality 8 by 8 images. And they did the same upsampling to 16 by 16, and they upsampled to 32 by 32, and so on, all the way up to 1024 by 1024. And after 18 days of training, they got these photorealistic images. Yeah? Yes. So they take this image, which is 1024 by 1024, and okay. Yeah. Yes, that's actually a great question. Her question, it's on the next slide, basically. I got a little bit ahead of myself. So what they actually do is, let's say for 16 by 16 images. So they've trained a GAN to generate good 16 by 16 images. They take the weights of that GAN, they add on another layer, which has new weights, and they originally essentially use mostly the weights from the old GAN. They have this thing called a grace period. So originally they use mostly the weights from the old GAN. But gradually, as the new GAN gets better and better at generating these 32 by 32 images, they start to weight more towards using the weights in the new GAN. And so at each layer where they progressively grow the GAN, they first use mostly the weights in the old GAN and then progressively use the weights in the new GAN more and more. So this is brand new stuff, and it works. Oh yeah, there's one actually interesting thing that sort of illuminates what GANs are supposed to do that the researcher that sort of highlighted, that was highlighted in this paper. So how do we score GANs? How do we know that these images generated are good? Like, what scoring metric could you use? Any ideas? It's not obvious at all. We can look at images and see how good they are, but it's not obvious how you score them. This is from Ian Goodfellow's tutorial from NIPS of 2016 on GANs. And I'll post a YouTube video to this. I highly recommend you watch it if you're interested in this stuff. It's 2 hours long, but it's excellent. And he says one of the challenges with GANs is there's actually no good scoring metric to quantify what it means for the generated images to be good. And it turns out, actually counterintuitively, if you just took generated images, looked for their nearest neighbor in the training set, and just subtracted the pixel values, GANs don't actually do much better than other image generation methods. They just sort of visually look better. And Ian Goodfellow mentions this in this talk. They don't actually do better than, say, variational autoencoders. They just generate images that sort of qualitatively look better. So what is a method that has been proposed? There's this cool thing called the Inception Score. And this was actually in the same paper that talked about semi-supervised learning. So what's the idea behind the Inception Score? Simple, cool, smart idea. So let's say you're trying to generate you're trying to build a GAN to generate MNIST digits. You know, so the digits you're generating should be 1 of 10 classes. Let's say that you then took these generated images and fed them through another network that was trained to tell which digit was in an image, a discriminator network. And let's say this other network outputted this as the result. It outputted this image you generated. I have no idea whether it's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Well, if that was the case, you'd probably think that this isn't a very good GAN. Maybe it's generating images that can somehow fool the discriminator, but it's not generating images that actually look like a 1 or actually look like a 2 or a 3, et cetera. So the way you quantify this is you say that this vector here should have low entropy. So it should not be the case that the images we're generating give us, you know, 0.1s across the board. It should give us like 0.9, like that's definitely a 0 you generated, and it should give us low probabilities elsewhere. That's one component of the Inception Score. The other component is this. Let's say we're training a GAN to identify or to generate MNIST digits. And every time it was producing zeros. It was producing perfect zeros every single time. So if you generated a bunch of images and then scored which image was the generated image most likely, if it came up 0 every time, that also probably wouldn't be a very good GAN, right? So the second component of the Inception Score is that if you looked at the most if you basically looked at all the images generated, and for each image you said, what digit is that most likely? That should actually have high entropy. That should spread out, like 10% of the time you should be generating zeros, 10% of the time you should be generating 1s, 10% of the time 2s, et cetera. So this vector here should have high entropy. And indeed, the authors of the progressive GAN paper, they generated CFAR10 images. This is another famous data set where you have 1/10 the images are cars, 1/10 are dogs, 1/10 are planes, and so on. And they showed that their model blows away all the other models using this Inception Score in terms of generating CFAR10 images. But you can't do this on this data set of celebrities. Why? Because there are no classes. It's not a like discrete number of classes you're generating. So they came up with this other metric, which is kind of cool. Basically, they sampled patches from the 8x8 images, the 16x16 images, the 32x32 images, and so on. And they looked at how similar those patches were at all these different resolutions to images in the training set. And the idea there was they were getting both a measure of, I'll just read from the paper, they explain it well. The distance between the patch sets extracted from the lowest resolution 16x16 images indicates similarity in large-scale image attributes, while the fine-level patches encode information about pixel-level attributes, such as sharpness of edges and noise. So they use that metric, and they score their GANs against a bunch of others and show that they're also better. So I think it's interesting to think about how you score these things. So finally, what is the future of GANs? So about a month or two ago, I sent Ian Goodfellow a message on LinkedIn, and he very graciously responded, and we've had just a few messages back and forth. And in one of the messages, I asked him, are you surprised by these results from progressive GANs? Like, do you think that, was this shocking to you or what? And his reply really surprised me. He said, I'm actually surprised how slow progress in GANs has been. Back in 2015, I thought that getting to photorealistic video was mostly going to be an engineering effort of scaling the model up and training on more data. I think this is totally fascinating because if anybody should have an accurate view into where the future of GANs and deep learning is going to be and what the likely speed of progress is going to be in the future, it's Ian Goodfellow. He invented the technique. He studied with the leading researchers in the field. He works at Google, so he should have really good knowledge on how difficult the engineering effort of scaling this kind of thing up would be. And yet, even he really has no idea how fast the progress is going to be. In 2015, he greatly overestimated it. Maybe he still is greatly overestimating it. Maybe he's underestimating it. We don't really know. So what is the future of GANs? Nobody knows. All right. I'll stick around for questions. Thanks, everybody.
So yeah, we can stay a little bit around. I mean, if you have any question, I can come with the microphone, or I can repeat the question. Anyone? Yeah, I will.
Wait. So I was a little confused about the generative and discriminative. So basically, you have two different networks. So are there two different set of weights for generative and discriminative? Because first during the presentation, I thought that the discriminative would be the inverse, or like that would be derived from the generator. Is it? Can you elaborate on that?
So I was wondering, we kind of have these two networks that we're training. Do you change the training process depending on whether you're trying to optimize for the discriminator or the generator? So like in the case of, generating these photorealistic images, you're concentrating on the generator. But in other cases, you might be doing it to, provide yourself additional training data for a discriminator. How does that change the training process of the GAN as a whole?
His question was, how does the training process change depending on whether your goal is to generate really good images or have a really good discriminator? And the answer is, your question was, does it change? The answer is it does change, but not by as much as you'd think. And the reason is, to have a good discriminator, you need a good generator, and vice versa, right? normally the goal of GANs is just to have a good discriminator. That's the traditional use case of them, to generate things. But in order to do that, you need the discriminator to be getting smarter as well. So, yeah.
You mentioned photorealistic video. Has there been photorealistic video applications yet? And so one thing I noticed was in those two examples you picked out, so for example, it didn't recover the back of her strap. It didn't. I think with the woman with the bicycle, some of the her looked like her shoe was kind of going in a weird direction. And so it occurs to me that if somebody were to try to use this for video, then some of the the physics that one would, the natural physics that one would want to expect in a video would be hard for the GAN to kind of to recover. Is that?
So, great question. The question was, like, could GANs ever do photorealistic video? Because they can't even do photorealistic images, and there's next frame prediction in videos, and if GANs are trying to do that, that could introduce other things. And yeah. Yeah, that's a really great and deep question. So his question is, correct me if I'm wrong, I think more generally, there's a question on this stuff of, do these programs have anything beyond a sort of superficial understanding of what an image is or not, right? Like, they don't know that a woman's wearing a backpack, so if she turns, the strap should always be on her shoulder, for example. And I think what people have started to figure out with this stuff is these neural networks really are just generating a superficial understanding of what is in an image, like at the level of textures and things, rather than a global idea of what's actually going on. And that's allowed people to come up with things like there's a whole field of adversarial examples. So you take an image and you tweak a bunch of pixels in a way that doesn't really change what's in the image. It's imperceptible to humans, but it changes what the neural network will output as the prediction of the image. So yes, it's a huge problem and a huge topic of research that neural networks don't really understand what's going on in images. They're just really good at picking out things like textures and so on. You had your hand up. Yeah,
I have a very simple question. Are there any other applications other than image analysis or image processing that you are aware of? Any other application domains than images?
His question is, are there any other applications of GANs other than images? I think this guy had some thoughts on that.